Okay, well, thanks very much for coming today. My name is Bob Westervelt, and I'm going to give you an overview of our Science Technology Center for Integrated Quantum Materials. This will be the first seminar in a seminar series, which is Quantum Materials and Devices seminars at Harvard. And the rest of the speakers will be people we bring mainly from the outside who are experts in this field. And they were chosen by the people in the center as people they particularly want to hear from. I think it's an excellent seminar series. We're going to be streaming this on YouTube so that if you'd like to, you're somewhere else other than Harvard, and you would like to hear one of these seminars, that you can simply go to the YouTube stream. Our center, CIQM, Center for Integrated Quantum Materials, has an agreement with YouTube to do that. We also have a channel, is the right word, on YouTube where we have videotapes, mainly showing the slides, from previous talks going back the last few years. And so if you would like to hear from somebody else, you can also find about that at another time. So our center is a collaboration between Harvard University, Howard University in Washington, D.C., MIT just down the street, and the Museum of Science at Boston. And the field of quantum and science and technology is undergoing sort of a second revolution. Back in the end of the previous century, the ability to use techniques like molecular beam epitaxy to make small layered structures that maybe were 100 atoms across and the like, allowed people to look at quantum phenomena at relatively high temperatures. But the idea of going down to things that were just the size of an atom, if you weren't an atomic physicist, was thought to be sort of impractical. And there are even entropic arguments where a single layer of atoms is not supposed to be stable. All of that sort of got blown up in a year, so to speak, in the year 2004, when Geim and other people were able to make single layers of carbon in a hexagonal lattice just by using Scotch tape, which is still works and in fact is still the preferred method for getting the highest quality samples, which is sort of amazing. You just keep pulling it with tape until it's the right shade of gray, and you're right there. And this is a picture of a graphene lattice here with a diffraction pattern that shows that it's really an excellent crystal. And in fact, graphene turns out to be amazingly strong, and you can stretch it about 20% before it breaks, which is not true of almost any other thing aside from fresh bread dough or something like that that you can think about. And it behaves very differently than regular materials. The electrons move as if they were photons with constant speed. The energy gap between electron and holes goes to zero. You see different sorts of quantum phenomena than you do ordinarily. And so the other thing that's done is that the temperature, when you go from, here's a picture of 22, this is a bit old now, CMOS, you can get 5 nanometer CMOS. But if you put an electron inside a box that size, and you make the wave function go to 0 at each side, and you ask what is the energy of that particle, it's about 1 millielectron volt, which is much greater than room temperature. 300 degrees Kelvin is right here. And so the quantum stuff is just not going to show up. And so in regular electrical engineering, all of this is irrelevant. You don't see it at all. It's impossible to use it for anything. But when you go down to graphene, you're near the size of a hydrogen atom, and the energy goes up to 10 electron volts, which is much greater than room temperature. And so it means using these materials, you can develop a device that's entirely quantum and that works at room temperature. And that's a very different game than developing regular electronics. Another thing that happens is that the energy of the transitions goes up to similar energies of electron volts. And it turns out that's optical photon energies. And so it moves the transitions that you're seeing from something down in microwaves and things that sound like exotic lab physics to something that you can actually see. And so that's another change. Another thing that came about is that particles are different. If you start in a vacuum and think like a high-energy physicist, particles you have are bare electron, photons, atoms, and the like. But if you go into solid state physics, a la Bloch and others in the 1930s, then you find that the particles amazingly move through a perfect crystal as if the crystal weren't there. But they do it very much like regular electrons, but now you get little bubbles of no electron, which is the hole, and they have a different mass than you would for a free electron. You also get a slower photon, slowed down by the index refraction, and you get a new particle of sound, which is called a phonon. If you rap on the table, you're creating a lot of phonons. And so we know this very well. But when you go to the quantum materials, you get a whole, it's like high energy physics and winning Nobel Prizes by discovering new particles. You find in graphene that the particles move, they're fermions like electrons, but they move at a constant speed. It's not like they have a mass at all. And electrons and holes are joined at a single point called a Dirac point. And they actually follow the Dirac equation as if they were ultra-relativistic electrons. Only you're holding your hand at room temperature. So it's very different. There's another thing called topological materials. And let me give my intro to topology. I used to have a cat. We used to actually have 5 cats at some point, which was mind-boggling. They would like to sleep on your face, and so you're like sleeping like that, and you go, oh, and you wake up and there's cat sleeping on your face. Oh no, and so you grab it and sort of give it a heave. But Isabel and I sort of got bonded, and she would rest in my lap. But she could take, and Isabel is just alley cat, regular tough cat, and then hold her up upside down, and you let her go, and she's like 4 legs up like that. Let her go, and then whop, and she hits my lap, legs down. And all cats can do that. You just throw them up in the air, and they do this thing, and they come down legs first, which is obviously a good thing if you're a cat. Then how do you do it? It turns out a mathematician called Marsden in Berkeley back in the 70s solved it, and it turns out that if I'm the cat, see if I can still do this without breaking my back, you can undergo a rotation, which is like you rotate from waist up in a cone, and waist down you don't move. And so that's what the cat does, is it whips around waist up, and depending on the solid angle that the half of a cat undergoes, the whole body twists. And this is an example of something that's called a Berry phase. You undergo periodic motion, and instead of everything staying the same, it changes, okay? And in classical physics, you can come up with a lot of examples. But in quantum physics, people said, well, that you get, with the Berry phase, you get a phase in the wave function. And they say, well, we don't want to deal with this, because in fact, we have absolutely no idea what to do with it. And so they threw it away and didn't solve it, but it's there. And it turns out that, I forget what the number is, 1/3 of all solid materials are actually topological materials where this Berry phase actually matters. And there's some examples where it's sort of a very strong effect that we use in the center. And so that's a whole new field of physics that was just previously ignored. It's coming back to life. And you can do things like in the quantum Hall effect, you can have edge effects if they're a strong perpendicular magnetic field where the edge effects go around of the sample, as shown here by the red orbit, where nothing's going on in the middle, the electrons just go in circles. But if you have a topological material, the strong spin orbit material in this class of them acts like a magnetic field and gives you edge states in 0 applied magnetic field. And so you just have a sample that you pick up off the table, and it's showing the quantum Hall effect just the way it is. And so this is entirely different than people are used to thinking about. And the third type that we work with is called color centers in diamond. Originally nitrogen vacancy centers, but other centers like silicon and germanium and even lead are interesting. And they produce colors, like a ruby is actually a chromium color center in aluminum oxide, Al2O3. But it's nice red color, but it works like individual chromium atoms are giving you that color, just one by one. They're far apart. And it turns out that in diamond, these color centers act like excellent quantum bits of information, the spin on them, even at room temperature. And this means that you can make bits of a quantum computer with not very much money that actually sit on the top of a desk. And in the advanced lab here, we actually have a device put together by Lucan's lab that allows the undergrads to do experiments on qubits just at room temperature without using optics. And see, these are all very different things. And so in our center, the vision, and let me tell you that for the young faculty, if you want to get money from the NSF, you have to have a clear vision. Not a long vision, but a clear one. And so the vision is to use atomic scale devices and systems from quantum materials to make quantum sensors, the easiest, quantum networks, a bit harder. This will take a few years. That's where you can make, using an optical network, for example, you can connect different cities quantum mechanically, and quantum computers that can really change the class of whether something's computable or not. And the idea to actually do this is sort of really mushrooming right now and creating a lot of interest in Washington, D.C., so much in terms of funding that I hope they don't overshoot it and then become tired. You want to sort of just the right level of progress, because some of these problems will take years to solve, others not. But I think it's a very exciting place to be. And so the quantum materials that we're looking at right now are atomic layers like graphene, boron nitride, moly disulfide. It's interesting, the materials here are actually high temperature lubricants, and you can buy them in spray cans. And if you have a motor that you want to lubricate so that it won't catch up, you use these because they flake very easily, and the flaking makes the thing slippery and works well. And so you can get some of these for almost no money. Topological insulators, which have these very strange surface states that run all over the surface without stopping. And then color centers in diamond. So at this point, I should say, since we can do this very informative, is anything that you want to ask me? I know a lot about this field. Questions, or be what I was talking about or not? No? Okay, but anything that I say, please let me know. What I'm going to do is I've given you sort of a broad motivation why to work in this field. Next, I'm going to tell you about what we actually do and give some examples of sort of current research, which gets to be pretty technical. And so at that point, I'm sure you'll have some things that you want to know about. And so why have a center? The idea is that nobody knows everything. And at Harvard, it's very important for the professors to actually appreciate that carefully in their personal lives. Okay? And so we have people who are really sort of world leaders in some particular topic, but then you take them too far away from that. And the truth is, not everybody knows everything. Some people are incredibly impressive, but it's still true. And so to go in this field, the materials are really either new or materials we thought were like high temperature lubricants, and like, who cares? We buy them for no money. It doesn't matter. But we need high quality materials. And to do growth and processing of these is very critical. And so you have to have people that really devote their expertise. It's a bit like cooking a puff pastry or something like that, only in a different field. You have to really absolutely know what you're doing to make the best stuff. And that's usually not known how to do that now. You need to make devices to fabricate them and characterize them. That requires a ton of money and new facilities. And at Harvard, thanks to a gift from Jeremy Knowles back in the year 1999, I actually wrote the proposal for it. We created the Center for Nanoscale Systems, which overall is about $250 million of building and facilities to do science in this realm, that is nanoscale quantum materials and the like. And MIT became intensely jealous and created an even bigger center called MIT.Nano, where it's something like $350 million being put into that. That will be more engineering. We should be more physicsy. Hopefully it will work out beautifully, like some yin-yang diagram where we're working together. But we have those facilities supported by the university, a lot of staff, and so we were able to actually make the devices, characterize the materials, and do that. And then the individual professors can do experiments, design a device from the new material, make it, test it, see how it works. Usually they don't work in the first time. Then you go ask somebody like Bert Halpern about what's going on for theory, and we have some really top-class theorists involved in the center. And by going around this loop, you know, being grateful for what you've learned and then correcting stuff you didn't know, that's the way that things actually work. Once I had, we got a new sample from Sweden that Linus brought, and he's working with my student, Anja Blazinski. The experiment worked in like 2 days, which I found hard to believe. But they actually won an award for it at the national meeting following that. But usually it's not like that. Usually it takes a few years for things to go. The reason why we got the money, and we just renewed about a year ago, is that the faculty we have are really superb. They're some of the best people in the world. Having them work together makes life good, and so you can find somebody that can answer your questions and help you out. So let me talk about the topics. We had a nice brainstorming session before the renewal went through, and again, for motivation, I showed them a picture from The Wizard of Oz, which when I was a kid it's still a good movie. You can see it. One of the first color movies. And what they're looking for is they're swept away by a tornado and placed in a strange place where everything is all of a sudden color rather than black and white. And she meets these strange people, but they want to reach the Emerald City. And in the picture, you can see the picture of the Emerald City up the top of the hill by following the yellow brick road. And to get the money, you have to say what the Emerald City is, and we did, like quantum computers and like. But then you have to also describe the yellow brick road by which you take steps. And this is what you actually do in the research toward the Emerald City. And maybe you get there and maybe you don't, but this is the way to do it. And so by doing that, we came up with the topics that the faculty actually wanted to work on. And this is coming from them. And what I did also is to put, in terms of these research areas, somewhat younger people who are sort of really known as being one of the top people in that field. And so in novel van der Waals heterostructures, the idea here is to stack 2D materials to make things that are more than one layer thick, and to do that currently with robots that stack whatever you want, peel it off, stack it in a controlled environment. And Philip Kim, who's famous for graphene, is the head of that. And what's shown here, and I'll talk about more later, is a bilayer of graphene that's a twisted bilayer. And what you do is, when I was a kid, we used to have a lot of mosquitoes. I was in Gibbstown, New Jersey, and tons of mosquitoes, more mosquitoes than you've ever seen before. We had mosquito screens to stop them. But if you take 2 mosquito screens, you rotate them, you'll get a moire pattern, like the one that's shown here. And it turns out that if you make the angle right, the electrons like to sit right where they overlap in these nice yellow spots. And they don't like to sit in the other ones. You've created another lattice inside the graphene that has remarkable properties that I'll tell you about. The other one is new topological crystals. As I said, many crystals are topological, and we don't really understand them yet. And so we have some powerful theorists who can dream up new crystals with new properties, but we need to find out how to make them. And like Liang Fu at MIT. And so to do this, you start with an idea, but then look into a materials database, find a real material that has that kind of band structure. Then actually make the material, look at the properties in electron microscopy or RPES or other things, see whether it works, and then you can make devices and go from there. And again, it's kind of a loop to make sure that this works. And Joe Czachowski at MIT is the head of that, and he's sort of a remarkable younger guy who knows MBE growth of these and other techniques to grow these kind of materials. Another one is if you want to make a quantum computer, the qubit that people typically use is an electron spin. And a 1 has the spin pointed up, and a 0 has the spin pointed down. And it can be sort of rotate between them, which is what makes it quantum. But the thing that screws it up is decoherence. Like if you come and have another particle bop it while it's pointed up, it'll rotate, and that wrecks the whole computation. And that's the big challenge that these people have. And it turns out that there are theoretically ways you can topologically protect the qubit so it can't rotate. It's like edge states in the quantum Hall effect are topologically protected because if they're going counterclockwise, I'm doing this, for you it's counterclockwise, it's good, around the sample, there's nothing you can do that will make it change direction. It just has the chiralities built into it. You can break the sample, whatever, and then you get two that are rotating the same way. And so that's topological protection. And so we have a group that's working on ways to make topological qubits to make these sort of quantum coherent computers possible. And the final one is based on color centers in diamond to make quantum networks. The Chinese have actually done a great job of advertising this by transmitting quantum keys using a satellite. And they actually launched the satellite and paid for it all. And it can take a quantum key from one place in China and send it somewhere else, but it's very slow. But the real idea is to have a fiber optic network where you have repeaters that are quantum repeaters, where they amplify without knowing what they're amplifying, which is sort of like, how can they do that? But theoretically, it's known. And then make a quantum network would, say, cover the US. And that means you could have a quantum computer in one place talking to a quantum computer somewhere else coherently without interference. And this is something that's actually coming along quite well. So let me show you some examples of how this works. Let me just show the whole deal. And the first one has to do with these moire patterns in twisted graphene bilayers. And it turns out if you twist them at a particular angle of 1.1 degrees, then if you calculate the band structure, this is energy versus momentum done by Tim Katsiris' group, there he is, then the energy versus momentum goes flat. And so what does that mean? If you change the momentum of a particle, the energy doesn't change. Normally, if it were a regular particle, the energy is momentum squared over twice the mass, right? And it goes, whoop, and it goes up. And with a regular particle, the Heisenberg uncertainty principle, delta x, delta p is equal to h bar. If you try to localize it, delta x gets small, then delta p gets big. And so momentum gets big, the energy gets big, and so you can't localize a particle too far or without supplying energy to do that. But if the energy doesn't change with momentum, that means that you can localize a particle down to some arbitrarily small size, and the energy doesn't change. And so it really turns on correlations, that is, interactions between different particles to form some pattern, because localizing them is for free. Okay? And people knew that in advance and then designed this material so it would do that. But what they found out was sort of two remarkable decisions, which made two Nature papers last year. One is if you vary the carrier density with the gate and back of it, and then vary the temperature, this is at liquid helium temperatures. When you half fill the band, it actually turns into an insulator. What happens is in that moire pattern that the electrons sit on the spots in the moire pattern, they don't talk with each other anymore, and it insulates. And so that was pretty exciting. It's a real insulator, which doesn't conduct very much at all. That was pretty exciting, and that was the first paper. But what was even weirder, though, is that if you, quote, dope it a bit by changing the density to be not perfectly filled, but some holes or electrons in there, it becomes a superconductor. And the resistance goes exactly to 0. And carbon, previously in a crystal, doesn't superconduct, period. And all of a sudden, you made carbon a superconductor by rearranging the atoms. That is something that's generated, what, more than 50 theory papers, none of which actually explains why it occurs. And so this is really a hot topic. It sort of created a new field of investigation. And whoever, I think Pablo Herrero is the one who sort of led this, along with some others, has already made him sort of famous and become more famous if this takes off more. It's an analog to high TC superconductors that also have an insulating phase, and then the superconductor is right next to them. But in some level is more simple, and it's more adjustable because you can change the density with the gate, whereas high TC materials, that's not so easy. And so this has really gotten to be sort of a big deal, and there's a nice picture of Pablo right here holding up something important. So, another area that Philip Kim and others have been working on, and this is Tim, Philip Kim, and why am I going brain dead? Tina Brower Thomas from Howard, is to do chemical intercalation of van der Waals heterostructure. The background is what carbon was used for decades, actually. People like Millie Dresselhaus, was to intercalate graphite with an I, is a layered material with a lot of strong layers that are held together by hydrogen bonds. And so if you put it in the right stuff, the molecules go in between the carbon layers, and it's called intercalation. And you can expand the material a lot by tens of percent and change the properties a lot. And that was a very active area. And what they're doing now is instead to start with just a few layers of graphene and then to intercalate it by pulling the material in with an applied electric field. And so it's electrically controlled intercalation. And the idea, again, is to make a new type of layered material that didn't previously exist and do that by design. And so this is coming along very nice. Bediako, who's the first author, got a job at Berkeley, which is always good. I used to go to Berkeley. It's a nice place. And this is kind of moving along. And there's another one which is kind of surprising, a recent publication, that if you have really clean graphene, you have an entirely new type of superconductivity that you see. And imagine that you have a regular material, and if you shine a photon on it, photon will create an electron hole pair, and the electron hole pair, suppose it's super clean material, that they'll just then move away from it in opposite directions. But in a clean material, it will go in any direction that you want, and so that there's no current, because some are going right, some are going left, some, so on and so forth. And that's normally what you see in graphene, too. But if you go to this magic point, this is a picture of the two crossed lines, a picture of the energy versus the momentum for graphene, that the two actually cross at what's called the Dirac point. And if you tune the density to set at the Dirac point, the kind of arrangement for electrons to sort of lose their direction goes away. If you have a lot of electrons, the Fermi levels above zero, the way that the electron would lose its direction is to just form other electron pairs. It will scatter with other electrons. And instead of going straight ahead, it will go slightly to the side. If it starts out in a particular direction, it will go that way forever. Even if it creates a lot of electron by splitting up, they all go in the same direction. Okay. This was predicted actually by Levetov back a couple of years ago. And so they've, again, Pablo working with others, Niobate, Jin Kong, and other people here, Tomas, Levetov, have shown that this works by taking a beam of light and then measuring the resulting current. And they found out when they put the light on a juncture where the shape of the material changes, the graphene, here's a narrow constriction, widens out, that they'll see light where the shape changes. That is where the electrons can, if they're near an edge, they can't go out of the material, they must go into the material. And if they go in a corner, then they have to go in different directions. And they've gone through the theory of this, and it all works out very well. And so it's a funny kind of a photocurrent by it opens up a new way to make devices where if you make the shape of the material have a particular kink in the edge, that you can create a current that's coming out of that kink that will go for many microns in that direction, which is sort of totally counterintuitive. Must be questions by this point. Is that totally, no? Okay. All right. Now let's switch gears and go on to the topology. I pointed out that this is something that's been with us. It's a classical effect, but it's actually a mathematical thing, so it's both classical and quantum. But the importance of it has only really been sort of appreciated in the past decade or so. And this comes from Joe Ciechelski, and he has nice ways to show things. And it shows that topology shows up in knitting. And so if you're going to knit a loop, and I used to be, my previous wife used to love knitting, and she made me an alpine sweater, which little kids used to laugh at me when I wore this, that had ripples across the top and all of that. So I know something about this. But here you are knitting away. You can knit with a topological twist put into the knitting stroke. And so when you knit a scarf in the loop, you make a Mobius shawl that's in the shape of a Mobius strip that has a half turn when you go around the loop. But you do that not by making that way deliberately, but you just knit each step, each piece of it in that direction, and you end up with a bigger thing has that topology to it. And it's sort of a nice home style illustration of what's going on. Let me show you an example of a new material that had a property that they wanted, and then they predicted what material to make and went ahead and did it and characterized it. And this iron tin material makes something that's called a Kagome lattice, which is actually, if you're making bamboo baskets in Japan, there's a particular pattern that they do that looks like a star, an iron star with a tin in the middle. And the reason they did that was to have a flat energy band where you can localize the electrons, where the energy doesn't depend on the momentum, and that's shown here. And to do this, it turns out the material turns out to be metastable and has to be grown in a certain way. And so Joe Ciechelski did that. But when he looked at the material, it looked sort of like a piece of coal. And they say, well, did we succeed or not? And you, hey, who knows? And they did transport on it. You see transport curves that look like rocks. And again, do you know anything? You know, not too much. But then we have an excellent set of high-resolution transmission electron microscopes at Harvard. And so we put it in the stem and then take a look. And you can see the crystal structure directly. And so you can see the layers in here, and sort of two narrow ones with big atoms and small atoms, and a little bit of offset, and then in between others. And if you look at the theoretical crystal structure on the right, as shown here, it's sort of a direct overlap. You can just put one on top of the other. And at that point, they became quite happy and realized that things were working. And since then, there's a technique that's called RPES, which is angular resolved photoelectron spectroscopy, that allows you to look at the energy bands, that is energy versus momentum, near the surface for material by blasting it with photons, and then looking what comes off. And by doing that with Ricardo Comin, who's a new junior faculty at MIT, they saw both on this material, they saw both the crossed bands and the Dirac point shown here, and they also saw the flat energy band that we've been talking about shown here in the real material. And so that proves that it actually works. I think this kind of technique, by putting together different groups and different tools, allows you to actually both make a new material, but actually understand what you've done. And when it works, you know that it works. Otherwise, if you had a piece of coal, you think, ooh, what to do? And so I think that will be very promising for the future. Let me show you. Okay. And so then the third area that we have is topological qubits. And to get back to topology, the type that you're probably familiar with is a donut. And you know, a donut has a hole in it, whereas a muffin doesn't, okay? And that's a topological difference. You could imagine the donut was made out of rubber, so you could pull on it and all that, but not break it. And then if you pull out a rubber donut, it's still a donut because it still has a hole. If you pull on the biscuit, it's still a biscuit because there isn't any hole. So that means that the topology makes it a very tough against being mashed around. And one of the first things that was seen, and actually got some awards, this Jagadish Madera, MIT, was to actually make a very thin ferromagnetic topological material. And that was the trick. And Jagadish knows tricks that other people don't know in order to do the molecular beam epitaxy in the right way. And in doing that, they were able to create a material that generated its own magnetic field. And so that if you look at the Hall effect as you change the density, you see something that looks like the Hall effect, where the magnetization flips abruptly, and then the direction of the edge states flips from going one way, let's say counterclockwise, to being one way clockwise as you flip it over. And so if you're thinking about transmitting a qubit, say at some place in space, and you want to transmit a coherent signal from one qubit to another, you need a quantum channel that you can't corrupt by having something hit it. And these edge states have that property. That is, you can't stop this current. It just flows 100% of the time. It's as if you have a hydrogen atom, the proton sitting there and electrons going around in a circle, and it'll do that for the age of the universe, okay? You just can't stop it. It has that kind of property. And Chang got a prize for this along with Madera, and it shows one direction that people are going. There's another one that happened recently, and all of these are things inside the center. But Hetchen Ren works with Amiri Kobe, did for her PhD work. And she's currently at Stanford as, Caltech as a postdoc. And this gets to be one of the current large challenges. And this is the following. It has to do with Majorana fermions. And what is that? See, I'll give you the fast version. Fermi, of course, is one of the best physicists in previous century. And in Italy, had a student called Majorana, who said that you can take the Dirac equation, which has electrons and rather particles and antiparticles, but when you go to solve it, you end up with imaginary wave functions. You can reformulate it so that you actually have real wave functions, but two of them. And they amount to mixing the particle and the antiparticle. It's like taking a superposition of the two. And if you've done a hydrogen molecule, you know how to impose the wave functions between the left and right parts of the molecule, and you get an overlap. It's done just in that way. And the particle becomes its own antiparticle, sort of like a photon. Okay. And each particle is a mix of the two antiparticles, that electron and anti-electron. And so this was, the beauty of that was appreciated for a long time, but nobody was able to see it because the experiment's just too hard because the energy involved too big, time scale is too short. So no results. But it turns out that if you take a superconductor where the energy scale is way smaller, it goes down to milli-electron volts, and you have a gap that's due to the superconductivity, that you have an electron and a hole. That is, you take a Cooper pair, you break it up into an electron and a hole, that you can do something similar. And this was predicted theoretically. But by applying a magnetic field, you can then take the material, the superconductor, see if I can do this with my hands. This one, somebody's bound to ask me a question, else you guys are smarter than me, okay? So that you have the electron in a hole, they put an in-plane magnetic field on, which creates a Fermi energy. That is just a elect spin, and a field creates the two Zeeman energy. As you turn the field on, split spin up from spin down. As the Fermi energy gets big, it kills the gap. And at some point, the electron and hole cross each other. And at that point, it becomes a topological material and not just a regular material. And so if you inverted the conductance and valence bands, if you like, in a regular material, that's the way you make it topological. And so what Hetchin was, and when that happens, then you get the magic situation that you'll have a long channel where you can put an electron in the middle, and the electron is actually a superposition of two Majoranas, say a plus and a minus, or an A and a B. You can separate them and put them on the opposite ends of the wire, and they're part of the same particle, part of their overlap of coming from a single electron that's an overlap of these two. And so they're topologically connected, but they don't have to be in the same place. And so you can move them quite far from each other, and then you can have a particle run into the one on the right, and it won't disturb the state that it's in. Okay. And so that's the challenge, and there's been some things, Charlie Marcus, Leo Kauenhofen, I think, was the first that saw evidence for that in nanowires. But it's still sort of up in the air because not everybody can reproduce the results, and there's a lot of arguments about how to do it. So what Hetchin did was to actually make it out of a two-dimensional material where this is changing the density and then the phase difference. And she's able to see the topological transition where if you're looking at the IDV, the slope of the current versus bias, the middle part goes from a node to actually being a peak. And showing this center peak is actually evidence that the Majoranas exist. And to really appreciate that requires a little bit of dedication to read the paper. But I think, again, this is important stuff that we'll be seeing more about in the future. Boy, that's a good question. Yes, I believe so. I mean, it must be because you're getting a spin out. I think the best way to think of the electron and the hole, each of which have a spin, and they're antiparticles from each other, and so they're very much the same thing. And if you just take a superposition as 1/2 of electron wave function plus hole wave function, 1/√2 is equal to the wave function, then you have a Majorana. That's the way that it works. But going the other way around, if you start out with all Majoranas, and they have the energy that's halfway in between. If you start out with a Majorana, then it could be separated into an electron and a hole by superimposing two Majoranas with the right phase. And so it works sort of like undergraduate quantum mechanics. So that part's not complicated, but the fact that it's an entirely new type of particle is the thing. And if people make this work, I think it's not easy. Turns out the way that you do the quantum computation is you have to braid them, much in the sense like that Majorana shawl was braided by having the electrons go in one direction, but they cross over each other either one way or the other. And then figuring ways to do the braiding is where it really gets interesting. But if you're in a two-dimensional system, then you can start to think about that. Whereas in a one-dimensional system, it's more tough. Other questions? Okay, and then the final one has to do, with color centers in diamond. And like I say, back when I was young, or your age, then color centers was a big deal for solid-state lasers. And one of the first optical lasers was a ruby laser back in the 1960s, because somebody at Bell Labs had the brains to actually do that. They pumped a lot of laser into a tube of ruby and put mirrors on the end, a lot of light from, incandescent, well, whatever, light from wherever they got it from, into the ruby, and it would actually laze and have coherent light coming out the far end. But finding the right color centers with the right properties was a big active field of research. And that was kind of figured out. And that's the way we got the lasers we use now. And we're in the same phase with diamond, only here it's realized that they make great qubits that are very highly isolated and coherent for long periods of time. Electrons for milliseconds and nuclei for many minutes, at room temperature. That it's extremely useful, and so people want to find out how to make this into a technology. And sorry, I should be looking at this one. Good. And so what we're doing now is looking at different color centers in diamond. And the first that was discovered is the nitrogen vacancy center, where if you have a diamond lattice of carbon, there's a vacancy at one place with the V, and there's an impurity, nitrogen, which has one extra electron, which is filling in one spot. And the way that works is like an isolated nitrogen atom, but it can't move around because it's been down. But in many ways, it looks like a single atom, like an ultra-cold atom. And that's the advantage of it. And people showed that you can get a spin up or spin down as coherence time of more than 3 milliseconds at room temperature, which is sort of amazing compared with other systems. But there's disadvantages in that it couples to phonons, which you don't want because that makes it incoherent. Solution is put silicon in instead. It turns out the silicon has 2 vacancies, one at the top, and strain-wise, instead of being a dipole, it's a quadrupole. And so it doesn't couple to the phonons very well, so that's a great advantage. And so there's a lot of work now on silicon vacancy centers, because the optical response is much more pure. And people are looking at other things, for example, germanium in the same situation as well as other materials. We've also looked at, not me, but the group has looked at other materials like silicon carbide and nitride materials to play the same game, so that the color centers don't have to go in, say, Al2O3 classically, but they can go in another material. And something that's very interesting is that Marco Lanchar, who is the head of this center, did with some collaborators in England, was to make something that's not diamond at all, but he made little posts using lithography, silicon posts, which they then draped a two-dimensional material over the top, and it gets strained where the top is, and that creates an optical quantum dot. And they showed that they can make that be a color center. So there's no diamond involved, and it's not even a crystal. Okay, so this is getting imaginative and sort of going in different places. And the field has gotten pretty advanced, is that the physics of how these things work, I think, is appreciated, and it's more the engineering of how do we actually make something and start a company and become rich level of work as opposed to just the pure academic version. This shows an example of what they're doing. Marco Lanchar is really an expert at fabbing things out of diamond. In CNS, we have ways to carve up single crystal diamond into suspended optical things. This is pure diamond. It's a it's a photonic optical cavity, and they go to New Mexico and implant a single silicon color center right in the middle. And they actually do this, and it actually works. And then they're making diamond chips with a number of these resonators on the chips that can be coupled with points to optical fibers to take it out of the doer. And the use techniques such as strain and sound to couple different color centers. And so they're moving, it's sort of like Intel in the year 1960, where they're trying to develop a planar process for silicon. They have the idea in their head, but they don't have it on the chip yet. And they're trying to figure out how to make it work. There's one thing that came out of it I thought was really interesting and sort of typical of the way that Marco works, is he's used to carving up a diamond, which is pretty hard material, and it's not that easy to do. And so they're really developing the technology. Is to look at lithium niobate. Well, again, when I was a kid, or your age, a lithium niobate is what the laser people use to modulate optical beams using voltage. And so you want to control a laser with pulses from a pulse generator. This is the way to do it. Except the pieces of lithium niobate were, big enough to hold in your hand, like 1 inch. And the trouble is it took kilovolts in order to do this. So you need a kilovolt, which is dangerous, a generator in order to turn it on and off. And what Marco did was to use this kind of diamond technology to make micron-scaled lithium niobate modulators using a similar technology in a single crystal lithium niobate. And then now, instead of using kilovolts, you can do it with 5 volts, which you get off your computer, and life becomes good. And this shows a picture of a modulator that was made this way, 2008. And since then, they've made an artificial optical molecule out of this technique, and going off and doing sort of amazing things. One graduate student did this, and I met the guy, and he said, look, this is actually, you may think this is something you just did, but this is actually, has a serious kick to it. And in fact, they went to a venture capital place, which I recommend to you, called The Engine. It started out at MIT. It turns out that industry found out about these chips and offered Wang $50,000 per chip that he would make if they would give them to the company, because they wanted them so badly, because it would just change the whole industry about how it works. And so they used this and went to The Engine, and they created a new company called Hyperlight, where they actually are going to, they got some millions of dollars to do the startup, and so they're moving ahead with this, and so that can actually go in practical direction. Okay, well, let me wind up. Boy, it's not quite 101, but I'll do this. I did, sorry. I'll start cursing, it's not appropriate. Once I was getting a phone reservation, and certain people do this by accident, and the guy started swearing like holy. And it just was his habit when things weren't going well. And I said, wow, they actually did a good job. But part of our challenge, an important part, is actually get young kids interested in the field, and it's create a community to do that. And so we work closely with Museum of Science. Carolyn Alpert there is terrific, and has really excellent ways of dealing with kids. Also with industry, the Engine looks to be particularly a good place to go for getting venture capital support. We also work a college network of undergrads to get them pulled in places like Wellesley into this kind of research, because they can see what it's like before they commit to it, to see whether this is what they want to do or not. Whereas some of these are gorgeous places to actually be, but then to see all the high-tech stuff, then it helps to visit Cambridge. And I'll show you a couple examples. This is one that came out of, and this is playing automatically. They made a immersion, here she is being immersed, thing that showed about topological materials, where you can see what the lattice looks like, and by using your hands, she's got two hands going like this, you can move around and see different parts of this. And 10 years ago, when I was teaching solid-state physics, I had some very low-scale versions of this. But this is great. You can reach up and actually grab the lattice, see like that, and rotate it and see the symmetries. It's looking like rows of corn when I was a kid. You start to see the planes, you know, and going on. And at the Museum of Science, we do things like this. And so this little girl here is sort of got the picture, and she's playing around with the crystals in her set. Museum of Science, fantastic for doing things like this. There's another thing is the deaf people, we got to know them for Gallaudet University in DC, is a university for the deaf and hard of hearing, are creating, they don't have signs, American Sign Language signs for scientific terms, like atom, there's no term. And so we have to spell it out like A-T-O-M, and it's so excruciatingly boring that people walk out of the room rather than look at the signs. And so they have a group of people, led by Gene Rice, Mandy Houghton, who are deaf people who are actually creating the signs for scientific terms. And I think this is fantastic because it creates a whole occupation for this class of people. And Mandy's great. She's sort of a deaf activist, like she spells deaf, D-E-A-F, in all caps, because they are, you know, better than the rest of us. But it really makes sort of a society of people helping each other. And this website that I've shown here, I recommend it. It shows English, but it can be all entirely in sign language, so you don't see any English at all. And so it's designed for deaf kids to learn how to do this. And another thing is to have impact, and in industry, and people can actually buy the products. That's what our company wants, our country wants, in some number of years. And so Graphenia moved from a branch from Europe to actually collaborate with Palacios Group at MIT. Element 6 is a diamond grower who loves Marco because he knows how to made a anti-reflection coater that wouldn't burn off by making a waffle iron in the surface of diamond, for example. And then the people at NGX who make sort of things you can buy. In terms of the quantum computing, there's two major efforts that are sort of in town, one at Lincoln Lab, led by Willem Oliver and his team. They have a fab there that can make Josephson Junction quantum computers right in Lexington. And Raytheon BBN in Cambridge has a group of about 25 people working on Josephson Junction quantum computers. And Harvard has seen the light and has also created a quantum initiative last year that's currently putting $3 million a year into postdocs and people in this field, and hopes to get more in the future. And the final thing is we have an annual workshop that's held in the summer. And next year's workshop will be in Valencia, Spain. And just to sort of interest you in this, I show some nice pictures. The site is shown right here. It's a large hotel right on the beach in Valencia, which is quite nice. I haven't been there. I've seen the pictures. It's the home of paella, which is good to eat. And this shows some pictures what it's to walk around. Spain is nice because it costs about half what the US does. And so this is actually quite, economical. And we have really an outstanding group of speakers, I think better than most international conferences because of the nice site and the fact we lined them up early, so I recommend this. And so that's it. I think we're sort of out of time, but I would be glad to take one question either online or sort of afterwards. No? Good. Okay, thanks very much.